guys, so today we're going to be in section 3.6. Let me screen share the notes with you. Again, you always have the option of opening up the notes on your own or having already printed them off or whatever you like to do with my notes. They're there to be a tool for you. So section 3.6 is the last section in chapter 3 that we are going to cover, and it's all about polynomial and rational inequalities. So a polynomial inequality is basically a polynomial equation, except that without an equal sign. You're going to have a less than or equal to or a greater than or equal to symbol instead of an equal sign. A rational inequality is basically the same thing, only rational, you need to remember rational means fractions. And so you're going to have a fraction with a variable in the denominator is what that means. But the first ones we're going to do are the polynomial inequalities. So I wrote out some really nice steps for you, and I wrote them out nicely in my notes, so I didn't want to write them on the board. So that's why I have the screen share. So there are basically 5 steps that you're going to do. Step 1 is you write the inequality as either f of x is less than 0 or f of x is greater than 0. So what that means is you're basically getting everything to one side of your inequality sign and having 0 on the other side. Step 2 is you're going to solve for f of x equals 0. You're going to find the real boundary, where the real solutions are your boundary points. And so that'll make more sense once we go through it. Step 3, you're going to locate those boundary points on a number line, like you graph them on a number line. This divides your number line into different intervals, is what that does. And then step 4, we choose test values that are in each of those intervals and evaluate f at that given number. So we're going to plug in that value into our equation and solve and see what happens. If the value of the solution is positive, then f of x is greater than 0 for every number that's in that interval. If the value of f is negative, then f of x is less than 0 for all the numbers in that interval. And again, this will make more sense when I start doing the examples, but it's nice for you to have all the steps so you can kind of check them off as you go through the problem. Step 5, you're going to write your solution set, selecting the intervals that satisfy the given inequality from the beginning. And you're going to write your solution set using the interval notation that we learned in 1.7, I believe it was, section 1.7, where you're using union or intersection, and you're using your interval notation where you use parentheses or you use your brackets. Okay, if you are still writing down those steps, remember, this is a video, so you always have the option to pause the video, or you can always just pull up my notes separately and look at them that way. I am going to get going on the example though, and I will follow all these steps so that we understand the process. So we're going to solve and graph 2x squared plus x is greater than 15. So step 1 says I need to isolate everything over to one side and get 0 on the other side. So in this case, all I have to do is subtract the 15 over to the left-hand side so that I get 2x squared plus x minus 15 is greater than 0. That's step 1, so I labeled it 1. Step 2 says I need to solve 2x squared plus x minus 15 equals 0, so that I can find my boundary points. So this is where you would FOIL. You're going to have your 2 binomials. I'm going to have a 2x and an x. That's negative and that's positive. So I'm going to have 1 positive and 1 negative. Factors of 15 are 5 and 3. So if I put the 5 here with the 2 and I put the 3 here, that's a really weird looking 3, then I'll get 6x minus 5x if I do it that way. Then I can solve for my binomials by setting them each equal to 0. So I have x equals 5/2 and x equals -3. Just as a note, 5/2 is like 2.5. We don't usually convert to a decimal, but I'm going to just write that as a note so that when I do my number line, it makes a little bit more sense. Because step 3 is where we're going to graph those boundary points on a number line. -4, -3, -2, -1, 0, 1, 2, 3, 4. -3, -2, -1, 0, 1, 2, 3, 4. So we had a boundary point of x equals -3. That's right there. And we had a boundary point of x equals 5/2, which is 2.5. So right there. So the reason we find the boundary points is because, as you can see, now we have like this section, we have the section between our dots, and we have the section to the right of our dot. And so we have 3 different sections now that we need to evaluate. Okay, so we're going to choose test values as step 4. We're going to choose test values from each of these sections and plug them into the original problem to see if we get positive solutions or negative solutions. So I'm going to plug in a -4. That's from this section over here. So if I have f of -4, I'm going to have to move you. Anywhere in the original, like once I got it, like step 1, anywhere in that I have an x, I need to write -4. -4 squared minus 4 minus 15 is greater than 0. 2 times 16 minus 19 is greater than 0. 32 minus 19 is greater than 0. And we have 13. Oh, we're doing it for, we set it equal? We don't have this extra thing, sorry. Because we're just evaluating at that point. So we get 13. That's greater than 0, right? So that means that our f of x in that interval is greater than 0. If we plug in any of these values in that interval, we're going to get a positive solution. So on my number line right there above that section, I'm going to write a little plus sign. Now I'm going to choose a point between my dots. And let me give you a hint. If there's ever a chance where 0 is in your interval, always use 0 because mathematically it makes it easy to plug in. So I'm going to find f of 0. So 2 times 0 squared minus or plus 0 minus 15. Well, 2 times 0 is 0 plus 0 is 0. I get a minus 15, which is less than 0. So that's a negative for this middle section. Now I'm going to pick a point from over here in my positive section. Since I did 4, the first -4, I'm going to do a positive 4 this time. Obviously, you could do 3, you could do 5, you could do 10, you can do whatever point you want as long as it's in that section. So I have 2 times 4 squared plus 4 minus 15. 2 times 16 minus 11. 32 minus 11, and that equals 21, which is greater than 0. So again, I get a positive. Some of you may be wondering, does it always follow a positive, negative, positive pattern? In general, yes. You're not going to have 2 negatives next to each other, and it will follow some sort of a pattern like that. So then what does that tell us? Well, what was the original equation? Once I got it in step 1, once I got it where everything was isolated, I said my equation is greater than 0. Greater than 0 is my positive sections. So on my graph, where are my positive sections? My positive section or interval is over here, and my positive interval is over here. So let's write those as intervals. My positive interval was from negative infinity all the way up to negative 3, including the endpoint. Did I include the endpoint? I don't include the endpoint. I'm sorry. The reason I don't include the endpoint is because it just said greater than. It didn't say greater than or equal to, so I don't include the endpoint. Over here, I was positive from 5/2 all the way to negative infinity, or to positive infinity. Now, dust it off, but all the way back from chapter 1, if I want to join two different intervals together, what sign do I use? What computation am I using? Am I using union or am I using intersection? I'm using union. Think of marriage. You union two intervals together, whereas intersection is what they have in common. So I union those two sections together. And then if you had to graph it, -4, -3, -2, -1, 0, 1, 2, 3, and 4. It's pretty much what you had already, except you have parenthesis, big arrow, scribble, 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 and then you have a parenthesis at 2.5. Basically, it's your boundary points. Scribble, 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 scribble. So here is your interval notation for the solution for this inequality. And here is your graph. You could also do your set builder if you had to. Remember, set builder is where you have squiggly x such that, and then you have to write an inequality for both of these. Well, what is this inequality? It says x has to be less than -3. Or, remember union, you use or, x has to be greater than 5/2. So those are the three ways you can write your solution out. Typically, you're going to write it in the interval notation, and then they're going to have you select which graph that matches. So you have to get everything on one side and have 0 on the other. Then you're going to solve like you would a regular equation to find your boundary points. You're going to graph those boundary points. You're going to pick a point from each section and find the solution, see if it's greater than or less than, mark it with a positive or negative, and then go back to your original and see if you needed the positive sections or the negative section to be the solution. Write that in interval notation, and you can also graph it. We'll do another one. All right, here is another example. We are going to solve and graph this. Here. I'm going to stop the sharing for this one just so I can make it bigger for you guys, and then I can reshare later. Now that we've seen how the steps work, you don't necessarily have to see the list, or you have your list in front of you. All right, so we have x to the third plus x squared is less than or equal to 4x plus 4. Step 1 says I need to get everything on one side and 0 on the other. So I'm going to move everything over to the left side. So I have x to the third plus x squared minus 4x minus 4 is less than or equal to 0. Step 2 says I have to solve this like it's an equation instead of an inequality, so I can find my boundary points. Now, way back in chapter 1, but also earlier in this chapter, we talked about how we graph these, or not graph them, but how we solve them. And the way we do that is we're going to group them. They're already, like, because we have 4 parts, we're going to look at just 2 parts at a time. two terms, and we're going to ask, what do they have in common? Well, x to the third and x squared have an x squared in common, and that leaves me with an x plus 1. And then I look at the next two terms, and I say, what do they have in common? Well, they both have a minus 4, which leaves me with an x plus 1 equals 0. When you are factoring by grouping like this, the whole goal is to get the same thing inside your parentheses so that you can pull out the parenthesis and you're left with just x squared minus 4. And then you're going to have a difference of squares. That's usually what pops up. So you have an x plus 1, an x plus 2, an x minus 2 equals 0. And then you find your boundary points as x equals -1, -2, and 2. If you don't remember this stuff, maybe go back and refresh yourself in chapter 1. Step 3, I'm going to have my number line. Let's see, I go all the way down to there. So -3, -2, -1, 0, 1, 2, 3, -3, -2, -1, 0, 1, 2, 3. But I had 3 boundary points this time instead of just 2, and that's totally fine. It doesn't change how I do the problem. I have a boundary point at -1. I have a boundary point at -2, and I have a boundary point at +2. The only thing that changes really is instead of just having 3 sections, I now have 1, 2, 3, 4 sections that I have to play around with. So that is what changes there. So I'm going to have to pick a test point from each of these 4 sections instead of just 3 sections. So step 4 is where you pick that boundary point. So I'm going to find f of -3 for this first one. So anywhere in the equation I have an f, or excuse me, an x, I'm going to write -3. -3 cubed is a -27. -3 squared is a +9. -4 times -3 is a +12. And then I will add them all together to give me a -10. That is less than 0. All I need to do is go up here and write that that is a minus in that section. The next one's a little bit more fun because our interval is just between -2 and -1. So we're going to have to do a fraction. And that's okay. I'm going to choose -1.5 or -3 halves. So -3 halves to the third plus -3 halves squared minus 4 times -3 halves minus 4. -3 to the third is still -27. 2 to the third is 8. Plus, I have 9/4. That 4 and that 2 will reduce down, so I get a +6 minus 4. Here's the thing though, if you're adding or subtracting fractions, you got to get common denominators. So I'm going to actually, +6 minus 4 is going to be the same thing as a +2. So common denominator in this case is going to be 8. Well, what do I do to the 4 to make it get to 8? I multiply that by 2, so I have to do it to the top. That'll give me 18/8. And to turn 2 into a fraction with an 8 on the bottom, I have to multiply the top by an 8 and the bottom by an 8, so I get 16/8. -27 plus 18 plus 16 is going to give me a 7/8. That is a positive number. So in here I have a positive. Sorry. Now I'm going to look at my next interval from -1 to 2. 0 lies in there, so I'm going to plug in 0. So I get 0 to the third plus 0 squared minus 4 times 0 minus 4 0, 0, 0 gives me a -4, negative. Then I'm going to do f of 3 to the third plus 3 squared minus 4 times 3 minus 4. 27 plus 9 minus 12 minus 4. And all of that equals a positive 20. Positive. So now which intervals am I interested in? Well, I have to go back to my original, like my step 1 equation or inequality. I had my linear, my x to the third plus x squared minus 4x minus 4 is less than or equal to 0. So where does that happen? Well, where is the negatives? My negatives are here and here. So those are the intervals that I'm interested in. So I am negative from negative infinity all the way up until -2. And in this case, I do include that -2 because it was less than or equal to. I'm going to angle that a little bit. So I do include the -2. The next interval that I'm negative on, so union, is from -1 all the way to +2. And again, I use brackets because it's less than or equal to. If you had to graph that, or had to identify the graph, -3, -2, -1, 0, 1, 2, 3. You have a bracket at -2, big arrow, squiggles. Then you'd have a bracket at 1, a bracket at 2. So this is a very small little area right in there. Whoops. I meant it's not that small. Sorry. It's over here at -1. So it's a little bit bigger area. And then if you had to do set builder, set of x such that, look at this first one, x has to be less than or equal to -2, or we have -1 is less than or equal to x, which is less than or equal to 2. There's the interval notation, there's the graph, there's the set builder notation. So when you're doing, you're plotting your points and you're doing the positives and negatives, just remember that if it's less than or equal to, then those are the negative intervals that you're interested in. If it's positive, as in greater than 0, greater or greater than, then those are your positive sections. Okay, so that's how we solve polynomial inequalities. Rational inequalities, you're really doing the exact same steps. The only thing that's different is you have some what are called like trouble spots. And I am going to screen share my notes again with you because there's some steps just like in the other one. So if you are going to solve rational inequalities, the first thing you're going to do, same as the linear or the polynomial ones, you're going to get everything on one side and have 0 on the other side. Then you're going to simplify it into one rational expression or quotient. Okay? Then you're going to set the numerator and the denominator equal to 0. Those are going to give you your boundary points. So when we did the polynomial one, we just had to set it equal to 0 and solve. This time we're going to set the top equal to 0 and we'll set the bottom equal to 0, and that will give us our boundary points. We locate those on the number line, we choose our test values, and we write our solution set. So that's really the only difference. And I'm going to leave the notes up for the first problem, and then I'll get them off so that you can see the board better. So we're going to solve and graph x plus 1 all over x plus 3, which is greater than or equal to 2. So step 1, we want to get everything on the left side. So I'm just going to subtract over that 2. We have x plus 1 over x plus 3 minus 2 is greater than or equal to 0. So that's step 1. Step 2 says we need to get one simplified rational expression or quotient. Right now we don't have that. We have a rational expression or quotient minus 2. And so we need to get the common denominator to combine these two. So for step 2, I have x plus 1 all over x plus 3. So what would be my common denominator between x plus 3 and 1? Well, it's x plus 3. So I have minus 2 times x plus 3 all over x plus 3. So what you do on top, you have to do on bottom. Greater than or equal to 0. Now I'm going to combine these things, and I'm going to distribute. So I have x plus 1 minus 2x minus 6 all over x plus 3 is greater than or equal to 0. So I have negative x minus 5 all over x plus 3 is greater than or equal to 0. At this point is where I have everything on the left side and I have everything all in one quotient. There's nothing else, there's just a top and a bottom. So from there, for step 3, I set my numerator, my top, which is negative x minus 5 equal to 0. And I'm going to set my denominator equal to 0, which is x plus 3 equals 0. I do that so that I can get my boundary points for my number line. I get negative x equals 5. I get x equals a negative 5. And I get x equals a negative 3. So step 4, I have my number line. I have negative 6, 5, 4, 3, 2, 1, 0. Negative 6, negative 5, negative 4, negative 3, 0. My boundary points were negative 5 and negative 3. So I plot those. And then just like before, I'm going to pick a point from each of my sections and find if I get positive or negatives. So in this first section, I'm going to pick negative 6. And I am going to plug that in to my step 2, simplified one quotient thing, one quotient term. So I have negative x, so it's a minus a negative 6 minus 5 all over x, which is negative 6 plus 3. 6 minus 5 over negative 6 plus 3 is a negative 3, which equals 1 over negative 3, so that's a negative 1/3. So this section is negative. F of negative 4, because I'm between negative 5 and negative 3. So a minus a negative 4 minus 5 all over a negative 4 plus 3. 4 minus 5 all over negative 1. Negative 1 over negative 1 equals a positive 1. So I get a positive here. In the last section, I'm going to use 0. 0 minus 5 over 0 plus 3 equals a negative 5 over 3, which is a negative. So going back to our step 2, I said negative x minus 5 over x plus 3 has to be greater than or equal to 0. That happens in this middle section here. So I won't actually have a union this time because it's only one section that I'm concerned about, or only one interval. I'm going to shift you down. So what is the interval? Well, it's the interval from -5 to -3. So this one said greater than or equal to. So in general, sorry, this is step 6. In general, we would write that as -5 to -3, like this with brackets. This is where the trouble spot is with quotients. With a quotient or a rational, what is the one thing you never want to see in a fraction? Hopefully you're saying, well, you never want to see 0 on bottom. That's correct. You never want to see 0 on bottom. So where was 0 on bottom for this one? Well, it's our denominator. Our denominator was x plus 3. And if that equals 0, we have a problem. And where is that? Well, that's at x equals -3. So if we let x equal -3, we have a problem. So instead of including that in our set, we are going to go up to -3, but we're not going to include -3. We're going to use a parenthesis instead because it causes problems for us at that point. Okay? So you have to watch that. That's like the extra step where you're looking for the problem spots at where is my denominator 0. Again, you can graph this. So at -5, we have a bracket. At -3, we would have a parenthesis, and it's all of that in there. If you had to do set builder for that interval, it would be the set of x such that, well, -5 is less than or equal to x, which is less than -3. Notice even when we write it there, we only put less than because we don't want x to equal -3 because that gives us a 0 in the denominator, which causes the problem. Okay. So I'm going to stop sharing and make this big for the last problem, which in my notes, I indicate that it's an extra example because there's sometimes that we don't get to it if I do this lecture in class, but since it's on here, you guys can watch it. It's going to be another rational one. So that way we had two polynomial inequalities and we have 2 rational inequalities, and we can get extra practice with that. So step 1, get everything over to one side. 2x over x plus 1. Let's track that 1 over. It's greater than or equal to 0. Now I have to get the one quotient, the one rational, and I do that by getting a common denominator. Common denominator would be the x plus 1. So I'd have 1 times x plus 1 all over x plus 1 greater than or equal to 0. So I get 2x, and I'm going to distribute that negative in, minus x minus 1 all over x plus 1, which is greater than or equal to 0. So I get x minus 1 over x plus 1 is greater than or equal to 0. There's my simplified one rational term compared to 0. Step 3, I'm going to set my numerator, my top, equal to 0 and solve. And I set my denominator, which is my x plus 1, equal to 0 and solve. So right here, if you kind of want to, like if you highlight or you use colors or you want to circle, this is our trouble spot. That's where the denominator equals 0. And so we definitely don't want to include that in our solution set. So if you want to indicate that earlier on, then that might remind you at the end to not include it if it's wanting you to include it or not. Okay, step 4, or I might be off on my steps. I don't know. Next step, we're going to graph using those boundary points. And I had a boundary point of 1 and -1. So I'm going to go -2, -1, 0, 1, 2, 3. So I had a boundary point at -1, and I had a boundary point at +1. So now I'm going to do my F, or I plotted a point from each of the sections. So I'm going to do -2, which will be -2 minus 1 over -2 plus 1, -3 over -1, which equals a +3. So this is positive. F of 0 equals 0 minus 1 over 0 plus 1 equals -1 over 1, which is -1. And I'll do F of +2, which is 2 minus 1 over 2 plus 1, 1 over 3, which is positive. But now I need to ask which interval am I interested in? Well, I'm interested in where my rational was greater than or equal to 0. So that's on my extreme parts, my extreme intervals. So that would be from -∞ all the way to -1. Now, can I include -1? No, it is my trouble spot. So I'm going to use a parenthesis. Union, +1, I can't include because it doesn't give me a trouble spot. Union, +1, all the way up to infinity. So if I needed to graph that, -2, -1, 0, 1, 2, 3. I'd have a parenthesis at -1, big arrow, squiggles. I'd have a bracket at +1, big arrow, squiggles. And if I had to do set builder, it's the set of x such that x is less than, oops, not equal to, less than -1, or I have 1 is less than or equal to x, which is less than -∞, or yeah. That's kind of a weird way of writing it. I don't know why I did that. If I look at this, what am I saying? Or x has to be greater than or equal to 1. It's kind of weird to write it in terms of the infinity like that. Sorry, I just got going. But that's it. That's it for section 3.6. So you do the exact same steps really for whether or not it's a polynomial or a rational. The only thing is you have to watch out for where your denominator equals 0 and make sure you don't include that in your solution set at the end.